Hi everyone, thank you for joining this webinar, In the Fast Lane, Simulation for Motorsport. First of all, a couple of housekeeping points. So all of you as attendees will remain on mute throughout this webinar, but that doesn't mean that you can't engage with us. Please do ask questions using the questions panel in the GoToWebinar panel. You can see a small arrow drop down where you can click and ask questions. We'd be very happy to answer those at the end of this presentation. Also, in a similar area on the GoToWebinar panel, you can access a white paper handout that you can download as a PDF directly from there to get some more information about how SimScale supports our automotive customers. All right, so yeah, I'm Steve. I'm your host today, and I've got the pleasure of being joined by one of our customers today, Andrew Richards. So welcome, Andrew. Andrew specializes in the design and development of racing engines, and he's responsible for all stock car racing programs at Ilmor. Andrew has 15 years of competitive racing experience, and he studied mechanical engineering at the University of Michigan. And when he's away from the track, he enjoys spending time with his family and making things in his home shop, like all good engineers. So let's have a look at what we've got to talk about today. So the agenda that we'll follow is we'll go through, first of all, some introductions, an introduction to Andrew and his background. And then I'll cover a very brief introduction of SimScale, and then we'll get into the actual application and introduction to Ilmor with Andrew presenting. And then we'll come back for Q&A and closing at the end. So yeah, really thanks for joining today, Andrew. As an engineer myself, also a mechanical engineer, it's great to speak to you and understand a bit more about your role at Ilmor. So how did you get into motorsport? It's something that's always interested me as well. And unfortunately, I went down the aerospace engineering route and now I'm in software, but I've always been interested by motorsport. So how did you get into it?
Yeah. First, thanks for having us on here, Steve. We really appreciate this opportunity to show the partnership that Ilmor and SimScale have created here and the power that it brings to our engineering projects. So thank you for having us and thank you for this opportunity. So yeah, as far as motorsports goes, you may have lucked out going into aerospace as opposed to motorsports, but yeah, for me personally, at least, motorsports was an excellent outlet for engineering, where my personal competitiveness, was able to mesh with engineering principles and result in designing, creating, developing these highly refined, high-performing, in my specific case, power units or engines, combustion engines. And motorsport provides a great opportunity, or in most cases at least, a great opportunity to prioritize performance, prioritize the solution in a real no holds engineering approach over something like cost or things like that. So it's from my standpoint, again, it really is attractive because you really bring out the best solution or something very close to the best solution with kind of a no holds mindset, whatever it takes to win sort of a thing. So
yeah, it's really interesting what you say about the ability to really optimize the end product that you're producing, because that's something that really struck me during my engineering degree as well. I did some work experience in heavy industry. It was in the steel industry in the UK. And every project I worked on was a cost-cutting exercise. And I really found it a bit disappointing as an engineer. I thought that I would be working on the cutting-edge technology and making the best possible products. And it was a bit of a blow for me as a young engineer, because I realized, actually, it's so much more about efficiency and cost. And that was when I got really interested in motorsport or aerospace, where there's a bit more leeway to produce kind of the most fantastic product that you can.
Yeah, exactly.
The other thing that I find interesting about motorsport, and obviously it's notorious for being a challenging industry in the field of engineering. So specifically for you at Ilmor, what does a typical engineering project look like, Andrew, and what challenges do you face on a day-to-day basis?
Yeah, I'd say in general, it's some unique problem set. It's usually, there's never a one size fits all sort of a thing. So it's usually some sort of solution that's very bespoke. Whatever the case may be, whether it's we're going to talk about water pumps later today. We're going to talk about pistons and those sorts of things. It doesn't matter what it is. It's almost always something very, very specific, something very bespoke, aimed at some specific problem case. And then once we kind of define what it is that we're going to be doing, this bespoke thing, getting it manufactured, get it designed, get it developed, get it manufactured in a very short period of time, get it out on the racetrack, and then start evaluating it. It's really, really quick turnarounds, and it's on something that's very, very specific. We don't do tens of thousands of things, but we can certainly do hundreds of things that are very unique, very specialized, and very high performing, and do all of that in a very short period of time.
Yeah, interesting. So it's all about the kind of cutting edge technology, but more on smaller production runs than you're talking about for an automotive supplier to the OEMs, for example, where they're more interested in producing something in very large production runs and as efficiently as they can.
Yeah, like I said, we'll talk about water pumps and pistons. OEMs probably make those by the millions, right? We make them more by, we'll say, the thousands, realistically, hundreds and thousands and that sort of thing. So a bit smaller, but again, very, very refined in what we do, very tight tolerance, very high performing. Just two different worlds.
Yeah, exactly. As an engineer, I find those sorts of things really interesting as well, because at the heart of it, we're often problem solvers, right, as engineers, and it's really a technical challenge to get over. And I've been fortunate enough to work with quite a lot of great customers now with SimScale and also in the automotive racing space. I know a lot about how we help our other customers, but it'd be great to hear from you about how SimScale is helping you with these challenges of these relatively small production runs and bespoke technical challenges.
Yeah, I'd say SimScale has really helped us to make simulation an integral part of our development exercises. Before we may have done some simulation, but there wasn't a lot of confidence in the simulation, or it was done with the knowing that there would be some factors that were not considered or some inaccuracies. And because of that, we would have these wide-ranging prototypes done, manufactured, a very, very large amount of time invested into testing and developing them to refine those prototypes to a final solution. Now, with SimScale, we're able to take these prototypes and evaluate them in the software, right? We're able to iterate them, we're able to refine them. We still make prototypes, but now, if the right answer is say the right answer is 5, the prototypes are 4.9, 4.955, 5.05. You know what I mean? Kind of right down in there. Whereas before we were more like, okay, let's do 1, 3, 7, 10, right? And you kind of sort of give a direction. But now we're very, very well aligned, very, very close to a final answer, and just do some final testing to hone in on the right solution, and more than anything, validate the simulation. So
nice. So would you say it's reduced the number of prototypes that you do, or do you still do prototypes for every project at the end once you've got a validated simulation that you think is a good solution?
Yeah, it probably depends a bit on the part, depends a bit on what the project is, but by and large, we will almost always do prototypes anyway. And like I say, it's more just to find the last, say, 0.5%, 0.1% to ensure that we are, really maximizing the performance of whatever that particular parts function is. And that's, like I say, SimScale has allowed us to be able to better understand what that final solution will be before making it, before, going down this empirical development path of manufacturing these wide-ranging prototypes and then kind of arriving at a rough answer. We're at a very fine answer now, with still some prototypes in there, just again to validate the simulation and make sure that we are getting every last drop of performance that we can out of the part.
Nice. Yeah, sort of on a slightly different topic, I guess motorsport is one of those industries that drives quite a lot of innovation, and that's partly due to the fact that it's quite a regulated industry, right? So there's always new regulations being brought in, and essentially all of the manufacturers are pushing the boundaries of what's possible within those regulations, and that usually brings about quite a lot of good technical advancement that follows through into the automotive sector. So what do you think is going to be the innovation, and what do you think the next 5 to 10 years will bring to the motorsport industry?
Yeah, like I say, the sanctioning bodies impart rules that generally drive some innovation, right? It's the restriction of the rules coupled with the creativity of the engineers that are working to those rules that result in some sort of real innovations that could be taken outside. And so I think we're starting to see kind of the early stages of what the future motorsport might look like, and that's things like increased hybridization. You look across the major racing series in the world, and there's a lot of them that have hybridization included in them. IndyCar is something very near and dear to us here. IndyCar is going to be bringing out the hybrid unit here in Mid-Ohio very, very soon. And I think Formula One's been hybrid for a while. You see things going on in rally car, World Rally that are hybrid. There's this myriad of things that are myriad racing series that are using hybrid technology, and you can also see it out on the road, not necessarily the same hybrid thing, but it is a similar technology and accomplishing somewhat similar things. So I think we'll see some of that. I think we'll also see the use of synthetic fuels as opposed to crude oil based fuels. Again, in IndyCar, very near and dear to us here. They're using sustainable fuels, the 85 with a 15% gasoline blend that's sustainable or sourced synthetically. We're seeing that in other areas as well. So I think a bit of hybridization, a bit of synthetic fuels, and further refinement of both internal combustion engines and further refinement of electric power units coupled to those engines, I think is what we'll likely see here in the next 5 to 10 years.
Okay, yeah, interesting. Be exciting to see what happens.
Yeah,
so
sure.
Yeah, let's push on through into the introduction of SimScale now, and I might ask you a couple more questions as we go through that, Andrew, on a couple of those points, and then we'll have a look at your use cases specifically. So what we're actually seeing from our other automotive customers, and this is more focused on automotive suppliers than motorsport, I have to say, but something that we're seeing in this industry is a push for much shorter lead times and much shorter response times for RFPs. So where OEMs may have been providing 4 to 6 months for an RFP response, we're seeing that they're demanding more like 2 to 4 weeks on that response time in the most severe cases. Are you seeing a similar trend in the industry? I accept that obviously the motorsport industry is slightly different to the automotive supplier one, but are you seeing a similar thing here?
Yeah, definitely. I think we're seeing things compress from, we'll say, weeks down to days for RFPs, and maybe even depending on the hours, where they're, hey, can you give me that by tomorrow? And the beauty of SimScale is that, if you're trying to get a rough idea of what something's going to look like, what something's going to take from an engineering standpoint, and ultimately cost, quickly creating a simulation, quickly running through some high level results to provide some guidance for those RFPs is immensely useful, and speeds things up on the turnaround time much faster than what we could have done before.
Okay, yeah, that's great. And what other tools do you use to support that process? How does SimScale fit in with other digital design tools that you've invested in?
Yeah, so obviously we have 3D design tools, right, to create the CAD bit of it, and that's kind of like the backdrop, that's kind of the foundation. So those tools are like a necessary thing, right? They're going to exist, for the purposes of creating the geometry. But once you get it into SimScale or any simulation tool, there's a lot of other information that needs to be added onto it for boundary conditions and materials and all these sorts of things, right? So we use some 1D solvers that have some 3D capability, but 1D engine specific software that allows us to get things like flow rates, allows us to get things like temperatures. It's essentially a virtual test bed for us that we can pull forces and all these other boundary conditions out of to apply to a part that's created in CAD that now exists in SimScale. Set up the boundary conditions and then use SimScale obviously to evaluate both the CAD and the 1D simulation. So kind of, SimScale kind of sits at the center, tying it all together and giving a final design, giving a final part. So yeah.
Yeah, and that's something we're seeing a lot more as a trend in the industry as well, as the use of system level modeling and 1D simulations that are fed with information from a simulation in SimScale and calibrated together. So that's really interesting. Okay, so yeah, if you don't know SimScale already, I'll just give you a very brief introduction to what we do and what makes us different. So SimScale provides a next generation cloud native simulation platform. And what this means is we have everything available directly through a web browser. All you need to access SimScale is a web browser connected to the internet. There's no management of local infrastructure, hardware, or software. All of that is taken care of. Also, we provide a single platform that has broad physics capabilities. So what does this mean? Well, it means that in one UI, in one project, you can have multiple simulation types, and that ranges from CFD to structural analysis to electromagnetics and thermal analysis capabilities. In some tool sets, if you know how to use the FEA structural analysis, you don't necessarily know how to use the CFD analysis. In SimScale, so long as you know how the physics works, the UI and everything all works the same way. Also, because SimScale is in the cloud, it operates at any scale. So this means that you can run as many simulations as you like in parallel, and you can scale it within your organization. So today, maybe I just want to run a simple FEA analysis in the morning, but maybe in the afternoon, I want to run 1,000 CFD simulations in parallel. I've got that capability at my fingertips. I can just do it straight away. I don't need to switch on any special HPC license or anything like that. And thanks to the fact that SimScale is in the cloud, it enables things like real-time collaboration. So if you want to collaborate with another user, even in a different geographical region, you just invite them into the project, you both log in to the same data in the cloud, and you're immediately able to collaborate and share data without having to share large files on a network drive or anything like that. And it also opens up the ability for us to support our users in live chats on the platform as well. Another differentiator of SimScale is the fact that SimScale is AI powered. Everything is AI powered these days. I think you can get a toaster that's AI powered. But this is really a strategic part of SimScale's development and SimScale's strategy. You can make AI predictions of what you expect SimScale results to be in order to iterate much faster at the early stage in the design cycle. So it really helps that left shift. And this is something that we're seeing a lot of traction for, specifically in the automotive industry, for these short RFP response times, to be able to iterate on the design a lot earlier and essentially produce a much higher quality product in the same amount of time. And some of the use cases that we support in the automotive industry, they're listed here, but really one of the most important things that we do and one of the highest impact things that we do is putting a high fidelity simulation tool in the hands of the designers at an early stage in the process. So that could be non-linear structural analysis for something like connectors or one-time snap fits, or sealing technologies if we're talking about structural analysis. It could be coupled conjugate heat transfer analysis for electronics cooling use cases. It could be frequency and harmonic analysis on a structural side, even including rotor dynamics, or various CFD and electromagnetic use cases. Normally, these sorts of capabilities aren't available directly in the CAD embedded tools, but we provide templated workflows so that design engineers, with the guidance of simulation engineers and solution experts, can set up and run simulations effectively and efficiently. Okay, that's enough of an introduction from my side on SimScale. I'd like to hand over to Andrew now to take us through the details of what he's been doing at Ilmor and what value they see from SimScale. Thanks, Andrew.
Yeah. All right, are you able to see our history page here?
Perfect, yes.
Yeah. Yeah, so just a short history on Ilmor. We started in 1984 with our founders, Mario Illian and Paul Morgan, creating a partnership with Roger Penske and his Chevrolet IndyCar engines. And then throughout the years, we have developed a myriad of engines. IndyCar, as I said before, it's kind of a mainstay for us, but a cornerstone for our company. We had involvement in with Mercedes through the 90s. And then in 1998, we built a U.S. facility that you see pictured there. That's where I am today. And we continue to develop internal combustion engines as well as other technologies, whether they be electric, battery, or otherwise, primarily for motorsport and also for marine. We have a large marine division providing power units for a variety of boat customers, tow sport, as well as stern drive customers. We have 3 locations. As I said, there's the stateside location in Michigan. That's where I'm at today. We also have a location in Mooresville, North Carolina. That is our marine manufacturing facility. And then Ilmor Limited in the UK, where they do race engine development, as well as design, manufacturing, testing over there. So we'll get into the SimScale examples that we've prepared. We'll start with a water pump simulation that we did. The objective here was to take a existing pump design that had a straight inlet, and some packaging constraints were driving a change to that inlet such that it was bent into the shape that you see here. And so these packaging constraints necessitated this change, and so we wanted to use our SimScale tool to optimize that bit of geometry and ensure that there was no significant loss in flow characteristics due to this change. We used the subsonic solver within SimScale to complete this, and we'll show here in a minute within SimScale how it was set up. But within the SimScale advanced concepts, a rotating zone was created to replicate the impeller. That's the red section there, that red disc that you see in that left side image. In addition, you can see a bit of the geometry progression here as we updated the design and used the simulation to drive some of these changes to the geometry through the area on the inlet there through that bend. Here are some of the results, and like I said, we'll get into a bit more. But this area here on the left shows that we have this dead zone, so to speak, here on the short side of the turn, where we have very, very low velocity, and that's really what we're looking to optimize to ensure that we're keeping flow attached, keeping a high velocity profile through there. And you can see as we optimized it, we arrived at something that had a very, very small low flow area around the short side with much more even flow distribution, much more even velocity distribution throughout the backside of that inlet on the pump. So I think this is a good time to jump over to SimScale tool. Or Steve, are you able to see my screen here within SimScale?
Yes, that's all good. I see that clearly.
Yeah, perfect. So here we have the straight inlet design. This is what we started with. As I said, we use the subsonic solver. So very simply bring in the geometry. This geometry was taken from a CAD model. It's created in SolidWorks, and we effectively created a solid region for everywhere where flow was taking place, everywhere where water was occupying. So you can see there's a water assignment in the materials. Everything in here is water. You will notice that the impeller is a solid within here, or is a bit of missing geometry in here. It's obviously not occupied by water. So the challenge becomes how do you simulate an impeller and simulate its rotation. And so that's where the advanced concepts comes in, where we have this simulation control. And within here, there's a rotating zone that is applied to this geometry that's created within SimScale, this disk area. This comprises the impeller, and you can see we're spinning at 4,725 RPM. So SimScale provides a great solution here to rotate that impeller within the simulation and provide a real simulation of the impeller and its dynamics. Within the subsonic solver, the mesh settings are a bit different than what you might be used to, where you're essentially setting up a coarse or fine resolution to the mesh at least within the automatic settings. The automatic settings were sufficient for us. We did have a region refinement here in that same rotating zone where we set a target cell size for the mesh. But otherwise, it's a relatively straightforward mesh setup here. Again, setting the fineness of the mesh within the automatic mesh settings, and then a region refinement in the rotating zone. So that is the straight inlet. We'll come into the first initial geometry with a turn. You can see kind of how the design began. Some of these early days simulations.
When you were modeling that, Andrew, were you going from the solid and creating the fluid volume, or did you actually adjust the fluid volume to put those turns in?
We were going from the solid. Yeah.
Nice.
So an animation here showing the particle trace and how that flow is developing around the bend. You can see we've got a bit of an eddy kind of forming around this bend here as it rolls around back into the impeller inlet. As mentioned a moment ago, there's a bit of a dead zone in the area on the inlet. So get that stopped here. and that's this here, where the flow is wrapping around this bend, but kind of packing in this back wall as opposed to following the short side of the bend. And so we get this area of a very low flow. We can use the inspect point tool here to see how low our flow is. Turn off this here. Let's see, we've got less than 1 meter per second, very, very low. 0.15 meters per second, very, very low velocity compared to something like the bulk fluid velocity, somewhere in this 4 meter per second range, something like that. So not ideal. Something that in the early part of the design we identified as an area to improve. So taking that a bit further through further revisions to the geometry here, you can see we've kind of extended that radius, pushed it out a bit to help develop the flow better, and continued on through that with some more iterations, a few more iterations yet, and we'll come into this second to last one here. Should mention on the boundary conditions, it was set up as a simple pressure inlet, pressure outlet. That's where the subsonic solver really becomes powerful. The more typical incompressible way of setting this up would have been to use some flow condition along with a pressure condition, whether pressure in, flow out, or flow in, pressure out. The challenge presented by that is you are effectively setting a flow rate as opposed to evaluating a flow rate. So what we wanted to understand was, as we make these design changes or as we add this bend to the design, how is our flow rate impacted? Using the subsonic solver, we can specify an inlet pressure, which is in general defined by the system. We can also define an outlet pressure that is very, very defined by the system due to restrictions that are downstream of the pump. With that, we can make geometry changes to the impeller, to the neck, whatever, and SimScale will converge on a flow rate. And that flow rate is really what we're looking to understand, as opposed to, like I say, an incompressible setup where you are effectively defining the flow rate. What's more is with the rotating zone, SimScale can also do a power calculation and evaluate what the power consumption is of this pump. So there's a lot of very, very useful tools here that we can take beyond just optimizing flow or optimizing geometry for the purposes of flow, specifically in that bend. So here was a final revision of it, where we have a very improved bit of geometry around the backside of that bend. As we mentioned a moment ago, our flow rate down in this area was sub 0.1 meters per second, well below zero. And you can see here we've only got just a small section where our flow is diminished, but in general the bulk fluid flow is occupying this entire volume, which is what we're after, and that results in a greatly improved inlet to the impeller. And an improved inlet to the impeller results in an improved net output or net flow for the pump. So yeah, that's the final revision over here, and we'll show a quick particle trace.
It's really great to see how the design evolved and how you were able to use the simulation to really gain some great insights here to get the optimum solution.
Yeah, it really it's really powerful and really useful for us, and yeah, it's part of what makes SimScale really powerful for us is the ability to do things like this and quickly arrive at some solution. The total time to end up here was we'll say a couple days to optimize this, as opposed to the more traditional design, make, test, redesign, remake, retest, sort of cycle that could take weeks. As you said, these days that sort of time is just not acceptable. So very happy with the way that SimScale is able to help us arrive at an answer much quicker. So
nice, that's really good.
Yeah. So we'll jump back into the PowerPoint here. That was the CFD example that we wanted to share. Next, we have a finite element analysis simulation that we want to share. This is for a piston. So our problem here, our objective to solve here was a crack that was found during testing in an existing design that formed in the crown of the piston. You can see over here on the right. This is a section cut through the transverse plane of the piston, and this crack formed from the crown down. And we wanted to use FEA to identify the high stress area here and understand what geometry was necessary, what updates to geometry were necessary to form a effective countermeasure to this crack formation. So within SimScale, mesh the piston using automatic sizing. And again, we'll like the water pump, we'll go over to the tool and take a look at that. And then a combustion pressure boundary condition with a fixed wrist pin boundary condition as well. The simulation identified the high stress area exactly where the crack formed, right here in this radius. The radiuses were modified and the geometry through here was modified. We were able to reduce the stress by 16%, which brought us below the fatigue stress and allowed us to have an improved life of the part, to eliminate the formation of that crack. So similar to the water pump, like I say, we'll come back into SimScale here. We'll take a look at the setup. So here the part again was brought in its 3D native geometry. We applied aluminum here to the material, fixed support to the upper half of the wrist pin bore to lock the piston down to replicate the support from the wrist pin. And then cylinder pressure was applied here to all the faces on the crown as well as the top ringland. Automatic sizing was used in SimScale. It provided more than adequate resolution for us. We increased the fineness from the default 5 up to 7, and this was the area that we were evaluating. So you can see we've got reasonable mesh fineness through this area. Certainly fine enough for us to find a hot spot or find a area of localized stress concentration. And so we'll open up the results here. So again, as shown in the PowerPoint, we identified these areas through here in the running samples, the samples that showed the cracks. As this is where the crack formed, and SimScale also predicted the highest stress in these same areas. So with that, we needed to develop some countermeasures, some updated geometry to combat that localized high stress area to reduce the likelihood of crack formation. So that led us to an increased radius through that bit of geometry, effectively increasing the area. We also modified the geometry through this little eyebrow here, where the two reliefs intersect, and so that was again applying the same boundary conditions, supporting through the wrist pin bore rather, and then applying a pressure to the crown as well as the top ring groove, and then pushing that into a mesh. Again, using the automatic sizing for the mesh with a setting of 7, provided more than acceptable mesh resolution in the area that we were concerned with, as well as over in here, this whole little area that we were evaluating. We did do a quick refinement here. Otherwise, actually, sorry, I just mentioned that we did do a local element refinement, just this one little area, and setting the edge length to 0.5 millimeter through here, actually, as opposed to using just the automatic, just to make sure that we had everything captured, make sure that we had maybe more than adequate resolution through these areas. So we'll open it up, post-process the results.
And that's the beauty of the cloud computing, right? You don't need to worry too much about how fine you're going. You can go as fine as you need to get the resolution that you require.
Yeah, I think that's really, for us at least, one of the key benefits of SimScale is the cloud computing allows us to have this simulation running on really any computer at any time, and you can, as you mentioned earlier, kind of stack simulations up. You know, if we want to try this at, you know, okay, now we're at an acceptable stress limit. Well, what pressure would it take to bring, you know, what pressure can we now run, cylinder pressure can we run with this updated geometry, right? So you can easily imagine a boundary condition with increased pressure and kind of stepping that up to see, all right, where can we go now? How much more pressure can we run before we encounter a crack? And setting up simulations very quickly, you know, just making a change to a boundary condition and starting those simulations and, you know, running off 5, 6, 7 iterations of this same geometry at new boundary conditions without having to make a huge investment in computing power, without having to tie up a computer for, you know, the better part of a day. And you know, to your point, Steve, you know, at whatever mesh resolution you know, you want. So that really is one of the biggest benefits to using SimScale over a more traditional approach that's running on a local machine is the cloud computing. You know, we can look at what we were doing there for you know, for any simulation run, but you know, the parallel processing power of the cloud computing is, you know, I'll hazard to say, you know, it's almost unmatched. It's extremely powerful from a parallel computing standpoint, and makes the software very attractive for that reason.
Nice. And with these results that you actually produced, did you do any physical testing, or did you then produce this piston and hopefully not experience the cracks that you did in the first design?
Yeah, exactly right. Yeah, so again, you know, kind of like we talked about earlier, creating those prototypes to validate the simulation, and they validated it. You know, the real samples, the real world samples validated the simulation. You know, very, very well. And they ran the same test as the piston prior without any cracking, and it's correlated very well and did exactly what the simulation said it would do. So yeah, we avoided this issue, or you know, solved this issue, better way to put it, and ended up with a better design. And again, you know, it didn't you know, require these multiple iterations. Well, how much can we run, or how little can we change the geometry? How much do we need to change geometry? All these sorts of questions, these empirical approaches that would have resulted in making multiple sets of pistons, running them through multiple tests, which is very expensive. And instead, we do it all in software and just do one confirmatory test to ensure that you know, we can check the box saying, yep, this is exactly what we thought it would be.
Great.
So yeah, that's the you know, like I say, that's the piston simulation there that we were able to you know, we use SimScale quite a bit for the finite element analysis. I think, you know, people, you know, maybe regard you know, simulation, they think of CFD and these, you know, these awesome, you know, fluid flows, or, you know, wind tunnel-esque sort of simulations, but it's certainly a powerful tool from an FE standpoint as well. And you know, it's not very core hour intensive or anything like that. It's very quick, and it's very you know, it does it very, very well with very, very good accuracy. So yeah, it's a very, very powerful bit of simulation within SimScale here.
Okay, brilliant. Yeah, so I'll just take back control, Andrew, and go back to the slides again, and give the audience a chance to ask some questions, really. We've got a few questions already come in. Please feel free to ask any more questions. If you've got questions about SimScale, or any questions that you'd like to put to Andrew about how they use the software or what they do at Ilmor. So I'll start off with the first question here that we had come in, and that is, was there any combustion chamber efficiency increase from the better cooling, or were reduced parasitic losses the main result from the water pump conduit optimization?
Yeah, the reducing losses or ensuring that we had fully developed flow, adequate flow to the impeller inlet was really the objective of the water pump exercise. It resulted in a fluid flow, like from a combustion chamber standpoint, cooling standpoint, all these efficiency storage standpoint. It resulted in a fluid flow that was nearly identical to the straight inlet, and that's really what we were after, was to make a packaging change, but not a efficiency change, if that makes sense. So accommodate the new package without having a significant impact on all of the other things that the water pump is affecting, things like the cooling of the combustion chamber and the efficiencies associated with that.
Okay, great. The next question is, I guess this comes down to the cloud aspect, really, and they said, have you ever simulated trackside?
Have you ever simulated trackside?
Yes, yeah, I guess talking about having your laptop there at a race or something.
Yeah, I'm not sure that actually I take that back. I think we have. I think we had a situation. This is some time ago now. Where we had a bracket failure. It's mechanical structural sort of a thing, where we had a bracket failure, and just out in the field trying to understand how did this happen? What initiated this? And it came down to a fastener load, improperly torqued fastener that resulted in a high stress, high contact stress with this bracket. And so we were trying to understand, what does it take for this thing to fail here is very, very uncommon. And with the team or customer there, right, kind of explain to them, look, this is what we think was going on, and here's some simulation results that back it up. Here's what we think the next steps would be to back off some of the clamp force that's being applied here. So yeah, actually, that I hadn't thought about that quite a while, but yeah, I guess we have. Yeah, it's not the norm. We would hope to have all the simulation work done in a nice refined product out there in the field at the racetrack trackside, but that's not always the case. There's always unforeseen things. There's always things out of your control, and so I guess there has been a case where we did a trackside. Yeah.
Nice. There's another question that I'll answer as well about the SimScale side. Someone said about the parallel simulations, can you run all of the different pressures in parallel? So yes, totally. In SimScale, you have no limit on the number of simulations that you can run in parallel. So when we're talking about the piston simulation, you could set that up as a parametric run where you sweep through maybe 100 different pressures and run all those simulations at the same time. Each simulation is started on its own dedicated AWS instance in the cloud, and then you get the results when it finishes. Okay, there's a couple more questions. I think the last one we'll have time to take is this one. When you guys are developing a new product, how far are your analytical solutions how far your analytical solutions change after a simulation analysis? So yeah, I guess how much do you change the design based on the simulation analysis?
Sure. Yeah, I guess it would depend a bit on the part and how close we are initially, right? So something that we, say pistons, we design many pistons very often, right? So we have a pretty good idea what it's going to look like. It'll be bespoke, I'm sure. Nearly all of our pistons are, but we'll have a pretty good idea of what that piston's going to need to look like from the get-go. And then as we do some analysis, refining that design is a natural progression to whatever the case may be, reduce localized stress in this example, or perhaps it's a stability thing or deformation thing where we're trying to improve stiffness in certain areas to ensure that we don't have excessive deformation, and so we will circle back through the designs and the analysis of those designs, the simulation of them, as often as needed or as much as needed until we arrive at the functional objectives that we set out at the start of that project. There's some piston designs we could, we've done where we have, over 100 iterations of designs in there as we try to, again, as I mentioned at the beginning, we're looking for the last 10th of a percent and getting every bit of, whether it's flow or stiffness or, reducing stress, whatever it is, it's, you got to chase every little bit sometimes to ensure that you have the best possible piece out there. And so, like I say, it can end up with hundreds of design iterations with the simulation associated to each design, and with other parts, maybe not as many because we're just closer on the first go around. But at the end of the day, it's really driven by what the functional objectives of the part are. If the functional objective of the water pump is to move X amount of water, we will iterate the geometry until we arrive there, and it may take 3 iterations, it may take 300 iterations, but the objective is the objective, and we got to meet it at the end of the day. So it's as many as needed.
Great. All right. Well, thank you very much, Andrew. That's been a great experience. I've certainly learned a lot about what you do and how you use SimScale. I hope everyone else has too.
Yeah, thank you. Appreciate the opportunity here, Steve.
Great. So just as a final next step note, if you would like to try SimScale or get started with SimScale, please feel free to reach out. You can reach out directly to me. You can see my email address here, or you can contact us through the SimScale website. Just go to simscale.com and you'll be able to get started. So thank you everyone for attending, and thanks again, Andrew, and we'll see you next time.
Thank you.